Good morning and then good evening, good night, everybody. Welcome to the second day of FRINGE 2021. We're happy to have you back. And we're going to continue with a session on advances on InSAR theory and methodological innovations. Before we start, we have 5 presentations this morning, and that will be followed by a Q&A session. So we would ask the audience to pose all the questions in Slido on the panel on the right-hand side of your screen. And if you do that and you have a question for a particular speaker, then please state the name of the speaker in the question so that we can, the moderators can know to whom the question is addressed. And yesterday there was a bit of confusion. So in Slido, you need to choose the session that you want to ask the question to. So make sure that and then you will see the questions that other people pose as well. The other thing I would like to point your attention to is that we will have a poster session later on today, where there are 32 posters or e-presentations, so also little presentations which are pre-recorded. And I would like to invite you to have a look at that. So without further much ado, I would like to give the word to the first speaker of today, Alessandro Ferretti from TRE Altamira, with a talk on amplitude SAR data. So Alessandro, go ahead.
Thank you. Thank you, Ramon. Share my screen. So here we go. It might sound a bit weird to speak about amplitude data in a conference about interferometry, but I think it's worth it because most of the time we forget about amplitude data. So let's start from the motivation, the introduction. We know the story, how we got here. We know the main problems in InSAR, phase decorrelation, atmospheric effects, rapid phase values. Then we found that their impact could be mitigated by multi-image, multi-interferon techniques. And consequently, over the last 2 decades, we've been working a lot to develop new multi-interferon techniques such as InSAR, SBAS, Squeezer. And so basically, we passed from the detection of surface deformation to the monitoring of surface deformation phenomena, from snapshots to time series, and from raster data to vector data. So in the end, what we deliver, what we generate when we go for a PSI analysis, typically, it's just a bunch of points, and for each point, of course, we have a time series of displacement data, and typically everything is just a package, a list of measurements, a vector file, and quite often the final data package contains no information at all about the amplitude values of the reader image. And to me, that's not the way to go because most of the time users are provided with this database and they start asking why, for example, there is a certain spatial distribution and not another one. And if you go back to the data, the amplitude data, would be extremely easy to explain the reasons behind why on a certain area you have measurement points and not for other ones. And in particular, you could immediately point the attention to, say, the low reflectivity areas or abrupt changes in the amplitude values. And this information can be extremely useful in interpreting InSAR results. But if we go back to the statistical model, when we started working on InSAR, you remember that it was extremely important to realize that looking into amplitude data, there was this Rice distribution, so with 2 limiting cases, Gaussian distribution for good PS and Rayleigh distribution for noisy pixels. We use the amplitude data and we are still using amplitude data most of the time, also based on the amplitude dispersion index or the signal to clutter ratio or even just the amplitude values. And that's good. I mean, even just looking into amplitude values, indeed, the probability of PS behavior depends on the signal-to-noise ratio, basically. So indeed, it's possible to already select, screen your data based on the radar cross-section, basically, of each individual target. So the question now is the following. Is it true that most of the pixels of a multi-temporal data set follow this statistic? We know that sometimes, yes, the answer is definitely yes. But let's try to look into the data. And we find something interesting also to provide more information for quality checks and whatever we have to do typically in a typical PSI analysis. So I'm going to use results from 1 year of Sentinel-1 A and B data over an area of interest. It's quite an interesting area where you have an urban area, agricultural fields, wetlands, say, and the sea. So this is a combination of dual pole data, of course. And if we look at the animation, say, with different amplitude images, indeed, you see that this is an area characterized by quite significant changes, okay? Even though, of course, for the urban area, you don't have much changes at all. So let's try to investigate the statistics. So if we run a typical normality test on the real imaginary part of different SAR acquisitions, VV, VH channel, indeed, we find confirmation that in homogeneous areas, water, say, or homogeneous agricultural fields, indeed, we have a Gaussian statistics. So most of the pixels would pass the normality test. But of course, for non-homogeneous areas, this is not at all the case. Now, if we run a Gaussianity test, a normality test on time, along the time dimension, we should be able to highlight the good PS candidates. And this is typically the case. So if you run, for example, the Shapiro-Wilk test along the time dimension, once again, you have both VV and VH data. Indeed, you highlight the urban areas, you highlight good PS candidates, but we see something strange because, of course, first of all, it's not that easy to distinguish between a Gaussian and a Rayleigh distribution. But apart from that, I won't go into the technicalities. There is a significant portion of data which does not follow the rise distribution. And it's characterized by, say, a long-tailed distributions of the amplitude data. So in this scatter plot, I've, say, reported the p-value of the Shapiro test and the amplitude stability index. So the ratio between the mean and the standard deviation of the amplitude data. So indeed, we can say that data are not homogeneous, say, in time. So the amplitude stability index is indeed a very effective tool to identify good PS candidates. But indeed, there are a bunch of pixels typically not following the right distribution. And remember, the dispersion index or the amplitude stability index is not a robust measurement. So even just a single outlier can impact heavily on its values. And indeed, usually the amplitude stability index values imply high temporal phase coherence, but the vice versa is not always true. But what I want to highlight here is indeed that low value of the amplitude stability index can be extremely interesting to identify areas affected by severe changes in reflectivity values. And a significant percentage of pixels do not follow the rise distribution. So we have something else, and we should try to highlight where we do not have a consistent, a homogeneous statistical population in time. And one of the possibility you have is also to run bimodality test. So you can read in the statistical literature about the modality coefficient, for example, but this is just an example. Once again, it's important for me to highlight that the data are full of outliers. And so that's tricky. And the number of outliers is much higher than what you would expect if all points follow a right statistics. So, and the question is, what's the impact of amplitude outliers on phase values? And I could show you hundreds of time series, thousands of time series. Indeed, there is a significant portion of the time series where you have a strong correlation between the amplitude time series and the displacement time series. So phase values, indeed, as expected, can be heavily impacted by an outlier in the amplitude time series. In this case, you have a displacement time series, amplitude time series, and the time series of the signal to clutter ratio, which is, you know, another way to identify good PS candidates. Unfortunately, this is not always the case. Sometimes you have a strong amplitude variation, but you don't have any visible, say, evidence of this impact in the phase values. And amplitude data can be extremely valuable also to identify the so-called semi-PS, because during a monitoring project, good scatterers can disappear, other good radar targets can become available, and so the statistical analysis of amplitude time series can then become an important tool for properly managing the temporary coherent scatterers. And this animation, I've just tried to report some examples, but again, there are really many pixels, typically even just in an urban areas, in a multi-year data set, you have changes. And it's very important to highlight where phase data we are reporting are not at all reliable. So the analysis of amplitude should be at least included in any key steps for quality check procedures before delivering PSI results. But what about DS? Okay, for distributed scatterers, coherence maps are usually considered, yes, the proper tools for PS selection. And again, we should really stress the importance of selecting the right statistical population to then estimate coherence values. And you remember that when we introduced a squeezer, we pointed the attention on the importance of selecting statistically homogeneous pixel before, say, running any estimation of the coherence to come up with the coherence matrix. Of course, there are different methodologies, but for all of them, it's quite important to recall that once again, we shouldn't forget about outliers. And so typically you need to include outlier removal algorithms before running these tests. Something which is not always, say, remembered is the fact that even if you want just to estimate the coherence map, you could look into intensity data only, so amplitude data, amplitude squared, and get a reasonable source of information about the phase. Because once again, amplitude and phase are two halves of the sky, okay, we fly in. So we really have to look at both amplitude and data. This is just, again, I mentioned to a very old paper, more than 24 years ago, when we were all young, but indeed it works. When you have in particular very high coherence values, you get a good image segmentation, even just forgetting about phase. And this can be extremely important if you have wrong compensation of local phase trends. So coming to the conclusions, again, rather than providing a set of recipes, we wanted to point the attention of all of you to the importance of a proper use of amplitude data, because amplitude data can be extremely useful to identify PS candidates, and we all do this, but also to highlight unreliable samples in PS time series, highlight areas affected by changes, and based on amplitude data, you can develop algorithms for semi-PS analysis and exploitation, and identify statistical homogeneous areas. And in general, again, don't forget about the possibility also to check your coherence values based, once again, on the analysis of multi-temporal amplitude data. And that's all from my side. Thank you, Ramon. Thank you all.
Yes, thank you very much, Alessandro, for a really very interesting talk. And indeed, we need to exploit the other half of the data that we're using, and I fully agree. So if you have questions for Alessandro, please post them in the chat window. I will move on with the next presentation, which is also about using additional data in InSAR technology, and that is using contextual data, and that is given by Mark Bruna. So Mark, please take it from here.
Yes, thank you, Ramon. Can you hear me well? Before
yes.
Yes. Okay, thank you. Good morning, afternoon, evening, everyone. My name is Mark Bruna, and I will today present to you my work on the storage and contextualization of coherent scatterers in a space-time matrix implementation. So in recent news, we have seen that subsidence and land deformation can often be viewed as a hot topic, both in the context of climate change, but also just with damage to buildings and property and to the natural environment. We see this topic pop up a lot in the news. For example, we see that the city of Mexico could sink up to 65 feet in the coming years. More research institutions are working on creating global subsidence maps. So this also highlights that subsidence and land deformation is a worldwide problem, which needs to be addressed by many. So here we see, for example, for the country of the Netherlands, that such maps are made. There are well-established modern InSAR time series methods, which can produce these maps with millions of measurement points, which show both persistent scatterers as well as distributed scatterers. For example, in this map here shown on the right, we see for the northern part of the country, for Groningen, that due to human influence, so the extraction of natural gases, the whole area is subsiding at a fast pace. But also in the southwestern part of the country, we see more natural causes for subsidence with the oxidation of peat, which is also partly man-induced. So concluding this figure, we see that a multitude of displacement characteristics can be observed, especially for the built environment, where the case study in this presentation will focus on. So there are many potential applications for the use of InSAR information, which could be the monitoring of infrastructures and buildings, but also analyze the effects of natural gas extraction or mining. But there are still some challenges with InSAR. For me, in the signal origin and interpretation estimates, we see that InSAR data is still quite complex, both in its acquisition and interpretation. We generally don't have a functional model, no stochastic model, and there's ambiguity in our phase observations. So we see that there's no one-size-fits-all solution for InSAR processing. This can be done in many different ways using many sources of data, both inherent InSAR data as well as contextual information, which could be anything that relates the scatterers to their physical environment, such as buildings or the soil, both deep and shallow. But still, the origin and depth of the displacement is not inherently known when we look at our data. So we don't know what is exactly showing the displacement. Could it be the object itself, so the house, its infrastructure or foundation? Can it be the shallow subsurface? Then we talk about Holocene to late Pleistocene depositions in the Netherlands. Or could it be the deep subsurface from middle to early Pleistocene layers, or even older? Here I show you a conventional InSAR output that we would see in our current state of the InSAR development. This map in particular shows an urban area for Rotterdam, the northwestern part of the city, with scatterers from Sentinel-1 ascending track 88. So here we show the line of sight velocity between a period between 2015 and 2019, where we see all these colored dots basically spread out on the map. What we would want to research or get out of the data is a more contextualized set of observations. So our proposed InSAR processing workflow relies on a feedback loop where we match up our conventional InSAR processing with contextual attributes. At the center node of this diagram, you see a space-time matrix, which I will explain later on. But this is implemented by means of a spatial database through which we input both InSAR deformation data as well as contextual information. So all the information which can be polygons or raster files which describe the physical environment. After we have set up this spatial database and the space-time matrix, we can query this to get either out of this the InSAR query output or a combination of InSAR and contextual information query output, which can both be fed back into either the processing itself or they can be used for the interpretation of the results later on. So as I described in previous slides, we have at the center node of this workflow a space-time matrix, which facilitates the data storage and the attribution and retrieval of our InSAR information. So this space-time matrix has two dimensions, space and time. Space is represented with the rows of the matrix and time along the epochs in the columns of the matrix. Then we see in this implementation that contextual attributes can be attributed both in space and time along both dimensions, so the m and the n dimensions, but they can also be queried in this way, which makes it useful for any data analysis or interpretation later on. And by doing it in a spatial database implementation, we get fast queries and fast retrieval of information, and also fast attribution of these contextual classes. So as I mentioned, we have a relational spatial database set up. In this instance, we use a PostgreSQL database, which gives a scalable implementation of the space-time matrices, and which combines data from different sources, which are maintainable and operable via structured queries, using SQL, for example. What is also an advantage of using the spatial database approach is that it enables spatial indexing, which leads to fast and efficient data handling, and it uses generally a generalized search tree, GIST, to retrieve the information that the user is interested in. And it uses minimum bounding rectangles to do so. In our research, we have set up this space-time matrix implementation in the following way, where we divide into separate modules the inherent attributes that are coupled to the InSAR information, such as the location in terms of coordinates, elevation, the linear velocity, and for example, the amplitude information, which is also important. Then as a second module, we store our time series, basically the deformation acquired per epoch, as double precision values, which are again linked to this first module with the use of primary keys, which all refer to the inherent point IDs that is given to each scatterer individually. And the third module describes all the contextual attributes that are attached to all the scatterers, which are also related with the use of primary keys and foreign keys to the other information. So storage is one thing the space-time matrix and the spatial databases can do, but its inherent use is in the use of data enrichment for scatterers. So we want to input contextual information in form of attributes, and this can be done in several ways. As I mentioned, we can do it in the space and time dimension or any combination thereof, so for a region and a time of interest. But we can also have random user inserts for which a user might think, oh, this scatterer should be labeled as such, as it might come in handy for my personal analysis or any further investigation as to the origin or the use of the scatterer. But also processing input or output can be fed to the space-time matrix as a priori information to get specific model parameters for the processing, either for the functional model or the stochastic model, as a means to switch the settings for our processing runs. And later on, we also see that our space-time matrix can be queried, and these queries can either be context-driven or based on the data-driven inherent information that is stored in the space-time matrix. Now we apply the case of the space-time matrix to do a general scatterer classification for the part of Rotterdam, which I showed at the beginning of my presentation. So we apply the space-time storage and contextualization methods to the northwestern part of Rotterdam for Sentinel-1 ascending track 88, with our observations from 2015 to 2019. And as a source of contextual information for this case, we use building foundation information as an operator for the stability that we see in this region, which comes from the funderingsloket for the city of Rotterdam. So on the left-hand side, we again see the map which I showed at the start of my presentation, where all the scatterers are exhibited along their linear velocities. And we see some variation over the whole city, with some buildings highlighted in red and others shown more moderately in green or blue, as they are a bit more stable. And on the right-hand side, we see our classification by means of the space-time matrix implementation of the same data set. But now all the foundation types are linked to each scatterer individually, which makes it possible to query them as such. So to get any outputs out of this space-time matrix implementation, we can run these queries on the different foundation types, which we see in the right-hand map. And the possible results out of this would be statistical analysis of these scatterers. On the upper image, upper left, we see histograms for the different scatterer classes. For example, we see here that the concrete labeled scatterers show a bit more stable behavior than their wooden or not founded counterparts. But they all seem to lie close together in this instance. We also see the same in the time series that is plotted beneath it, where we still see some variability in our results. But we still see this general trend of concrete foundations subsiding less with respect to our wooden foundations or our non-piled buildings. So this is one type of output we could get from the space-time matrix implementation. But this can also be used to combine different attributes into a single search. For example, if we would be interested in scatterers that are founded on concrete, but still have, for example, peat subsoils underneath it, the same type of query could be applied. And this could be compared to, example, buildings with a combined foundation that are well founded on more stable sandstone layers, for example, on the deeper subsurface. So concluding, I have shown that we have a space-time matrix implementation for InSAR observations, which can be attributed both in space and time with contextual classes. This can be done in a scalable way, which allows for fast and efficient queries which make use of spatial indices to retrieve the data. And with combined searches, and we are now also working on machine learning algorithms to go through this contextual combination of our InSAR information, to do this in an automated way, to detect patterns in our scatterers for different classifications, which describe the physical environment. Thank you for listening. And if you have any questions, I would be glad to answer them in the later part of this session. Thank you.
Okay, thank you very much, Mark. And indeed, please post questions again in Slido. We'll move right ahead with the next presentation from Alberto Refice on model-free characterization of low-noise nonlinear MTI time series. So Alberto, the floor is yours.
Hi. Yes, can you see my screen?
Not yet. We see you.
Just a moment. Okay. Okay. It should appear. Okay. So it should be fine. Yes.
Yes, I think we see it this way. Yeah. Go
okay.
ahead.
So good morning, everybody. I'm Alberto Refice from CNR from Bari, Italy. I will be showing this presentation. I would like to acknowledge my co-authors Fabio Bovenga and Guido Pasquariello, also from CNR. So this is the outline of my talk. I will do a little introduction about digging information in MTI and InSAR time series. Then I will try to see what we actually look for in an MTI time series, looking for. So, and I will briefly introduce the concept of fuzzy entropy. Then I will show some results obtained in simulations, and then some toy examples from some real data, and then some conclusions. Okay, so we have seen in this conference that multi-temporal InSAR provides time series of target displacements, as we have seen over even very large areas like entire nations, continents, or even globally in a foreseeable future. Most algorithms use a merit figure to characterize targets, which is known as temporal coherence, which can be defined as the vector sum of the complex phase residuals with respect to a given model trend. Okay. So as a consequence of this definition, the phase residual can be theoretically thought of as the sum of the contribution of contribution due to noise, plus another systematic contribution due to the adequacy of the chosen model to describe the actual displacement trend. And of course, we are neglecting here other processing errors which can be also present. So if and only if this systematic bias can be considered negligible, then the coherence is a good estimator of the phase noise. Otherwise, this estimator is biased. So, we see that by selecting target with high coherence, we select basically the trains which follow the assigned model. While in practice, we see that once a model is assigned, then low coherence targets include both actually noisy targets and targets with low noise, but the wrong model. So, and we could be actually interested in to see these targets. So okay, suppose you are, let's say, a technician working for a city authority or in charge for the safety of buildings or infrastructure. Okay, so you are typically given a map of PS targets like this with the one. So of course this is a limited area, but you can imagine the same reasoning applied to much larger areas. As we know. So these are PS selected with a gamma, the temporal coherent threshold of 0-point height, but with the usual linear model. However, you are actually interested in nonlinear trains, which could indicate troubles, for example, like failures or strong seasonal displacement due to temperature or other types of hazard. So, okay, you can ask your provider to give you the data set with a lower threshold, and then the provider gives you this kind of map with almost all the pixels in the image, which are obtained with a very low threshold in this case, for example, 0.1. So you have all these points more, all this with gamma less than 0.8, from which you are planning to extract all the relevant ones, that is the ones with the nonlinear behavior. So, what can you do with this? You can start fitting, for example, linear models, which with a low linear coherence may look like this. Then you can go on fitting higher order polynomial models like quadratic models, cubic, and then you can go on fitting, for example, seasonal models and so on. So you will have to do quite a lot of work. Of course, you can also use combined models, and you can fit a whole big library of models, and we have a poster on some rigorous procedures to perform such operation in this session. But the point is that you are likely to have to spend a lot of time, which for huge quantities of PS, this may end up as a real bottleneck in the exploitation phase. So let's instead focus on what we actually look for in a time series to consider it interesting. Well, the simplest answer is that you look for at least some interval of time in which the function is smooth. That is, it has small variations from one sample to the next compared to the entire variation. So this means that in practice we are looking for order, which to physicists like me naturally leads to the definition of entropy. Okay, so what you can do, you start digging into the literature for methods to measure entropy in time series. And you invariably stumble into a series of connected definitions all developed in the context of medical data analysis. So without delving too much into mathematical details, here we just sketch some definitions which start from what is known as sample entropy, which considers short subsequences in a time series, and comes the ones which are similar according to a simple distance function. Then the definition can be fuzzified by introducing this function, capital D. And so finally, we end up with this definition of the fuzzy entropy as the logarithm of the ratio between these average distances between short subsequences of lengths m and m+1. So the main point is that in the literature, low values of the fuzzy entropy are usually associated to regular time series. Okay, we now observe that we can slightly modify the definition of the distance, which is original, the Chebyshev distance, and this can be adapted to work with phases so as to avoid the effect of wrapping jumps. So basically, the main point is that to estimate the fuzzy entropy, you need to set some parameters, which are the length of the subsequences considered m, the r parameter, which controls the distance function, which is usually defined relative to the time series standard deviation, and then the exponent of the fuzzy function, which is usually set to 2. So we will stick to this value as well. Okay. So, but how does this all apply to InSAR? So, which parameters should we choose? So, what we did is to perform a series of simulations, creating time series, which are the sum of a library of models plus white noise with a fixed variance. Okay, and then we estimated the fuzzy entropy for each of these simulated time series with a set of parameters to study sensitivity to noise conditions. For each set of parameter, we simulated 10,000 samples. So, okay, here we plot, for example, for one model, the trends of the fuzzy entropy as a function of the noise standard deviation with respect to the signal one. For different value of the R and the M parameters, we see that although the values of the estimation vary as a function of the parameter, the general trend is mostly stable, with a monotonic increase of the fuzzy entropy with increasing noise until leveling off to a plateau. Here in the bottom left plot, we see how the fuzzy entropy is a good estimator of the true coherence, that is the coherence computed by subtracting the true model instead of the coherence obtained by subtracting the linear model, which we know is biased. Okay, so this general result, this monotonic increase with noise, is valid for practically all the considered models and even their combination. So what we end with is this fact that once you have fixed a set of parameters, the general trends of the fuzzy entropy estimator is practically the same. It decreases with the decreasing signal noise, without having to specify the signal model. An interesting case to be added here is the case of a temporary PS, which is born at some time during the monitoring interval. We see that in this case we varied the time of birth of the target instead of the noise level, and we see that in this case the trend is also monotonic, but especially for higher M values, the fuzzy entropy stays quite low for birth time very close to the end of the monitoring period. So this means that the fuzzy entropy is particularly good at picking temporary PS, which are born very late. Of course, the same conclusions are valid in the time reversed case of the death of a PS. Okay, finally, we have seen so that the fuzzy entropy is a good indicator for the presence of noise without having to specify a model first. But how can we further characterize this indicator? Can we attach confidence intervals? Well, we did not find any closed form distributions for the fuzzy entropy in index from which we could extract confidence intervals. So we recurred again to simulations. Again, we simulated noisy samples as before, and we selected the ones below some threshold value for the fuzzy entropy. Then we counted how many of these selected samples actually contain more noise than expected, say more than 0.5 as a noise to signal ratio. In this way, we obtained empirical performance curves for the probability of exceedance of noise levels for any threshold value. We can see here that these curves are again mostly superposed for all the signal models once you have fixed the estimation parameters. So, for instance, we see that for m equal 2 here, by using a fuzzy entropy threshold of 0.65, we expect not more than 5% of false alarms. Okay. So now let's quickly return to the previous example and see what happens if we isolate the targets with values of fuzzy entropy below the threshold corresponding to a false alarm of, say, 5%. We see that this indicator isolates a relatively low number of targets, around 2 to 3 orders of magnitude less. And if we look at the selected time series by this indicator, we see that all these targets mostly show what we have deemed as interesting trends. We have seasonal trends, partially seasonal steps. We have targets which are born or die at certain times. We have something like exponential decreases and so on. So all these targets are, of an interesting kind, and so they are much more manageable to analyze in a further step that having to deal with the whole data set. So we argue that the index of fuzzy entropy is a good tool to be explored in the future for the characterization of large MTI time series maps. Okay, so these are my conclusions. We have seen that selecting the interesting MTI InSAR time series is difficult because the most used merit figure, that is the temporal covariance, is model dependent. Fuzzy entropy is a measure of disorder in the time series, so it quantifies the irregularity and then the opposite, which is the regularity of a time series, without specifying any model. We have seen in simulations the performance of this fuzzy entropy index, and we set up also some approximate confidence interval, and we have shown some toy example taken from real data to show the capacity of the fuzzy entropy to isolate small sets of points exhibiting interesting low noise, nonlinear trends. So such a smaller data set can be cataloged in a subsequent phase. The computational cost is quite low, is of the order of n log n. It must be said that this type of estimation is not appropriate for a time series less than 150 to 200 samples. So it's most for Sentinel-1 or Cosmos Chime at very populated time series. And so we are working at further studying this index to see if we can integrate it within existing MTI InSAR processing chains. That's all. Thanks. Let me just invite you to my special issue and do some acknowledgement for data processing to Raffaele Nonticato and Davide Nitti. Thanks again.
Yes, thank you very much, Alberto. A very nice talk. And I think what all these three talks until now have in common is that they acknowledge that of all these millions of measurement points that we have, that they all behave in a different way. And we need to find out how they behave to increase their the interpretation of them. So this is a great contribution to that. Thanks. So we will move right further with a talk of Mario Costantini entitled Optimal Fusion of Ground Deformation Measurements from Different Sensors. Mario, the floor is yours.
Yes. Okay, can you see my screen?
Yes, perfect.
Okay, so I'm going to present a technique for fusion of ground deformation measurement from different sensors. As we know, there are more and more InSAR satellite missions. Many were already launched. Many other will be launched in the next future, in the near future, among which we will have also the SAR microsatellites, which promise to revolutionize Earth observation and InSAR with a huge amount of data. So in this scenario, we believe that it's important to have a method for integrate together in a robust way the different measurements from all this InSAR mission, and also to integrate data from GNSS and other technologies. This task is not completely trivial because different sensors with different acquisition characteristics are not directly comparable. First of all, the component of the three-dimension actual measurements that is measured is different, depends on the acquisition geometry, because as you know, SAR measure the deformation along the line of sight. Also, we know that InSAR measurements are relative measurements, so we have different references in space and time domains. Different measurements can have different and irregular spatial and temporal samplings and resolutions. And finally, we have normally we have different coverages, different areas, and temporal spans covered by different stacks and InSAR processing. So what we want to do is, first of all, to refer all the different measurements to a common temporal and spatial reference, to reconstruct horizontal and vertical components of the ground deformation, at least when multiple ascending and descending geometries are available, to optimally integrate external measurements, in particular GNSS, but in general, any kind of external measurements. The method also makes it possible to reduce noise in the areas of overlap, but this is not the main point. The main point is to obtain an optical mosaicing in the remaining areas. It's also interesting the possibility to remove some large-scale systematic errors that we risk to have in InSAR processing, because when there are very large scale with movements with a big spatial extent, if the area of analysis is not big enough, since we have to remove atmospheric and orbital artifacts, it's difficult to distinguish real signals from these artifacts, and the type of filtering that we make depends on the extent of the analyzed area. And so if the analyzed area is not big enough, we tend to remove the signal, the actual signal. So the idea is to combine all together to all the measurements together. So assume that we have different independent processings, InSAR processings, for example, different stacks, but in general, we could also have clusters that are smaller than an entire stack, because maybe we processed a smaller area, or simply because we don't have, we were not able to connect everything, and we have more than one reference point. So anyway, given these clusters, the first thing the algorithms make is to match the corresponding measurements in the area of overlap, and to define a common output spatio-temporal grid, not necessarily regular. Then the algorithm exploits the fact that the displaced measurements of each cluster must be consistent with each other in the overlapping areas, and also, when available, must be consistent with in situ measurements. So the algorithm exploits this information to align the measurements in the space domain by applying a parametric surface slow variable in the space domain to the measurement of each acquisition date of each cluster. Align the measurements in the time domain by applying a constant to each point of each cluster in order to refer the cluster to a common reference time. And finally, tie the deformation measurements to the available ground truth or ground references. In formulas, there are two main equations. The first equations tell you that if we denote with R the InSAR deformation measurement along the line of sight, then this should be equal to the component of the actual deformation D along the line of sight, plus a temporal calibration constant, and a spatial calibration surface F. This equation is of course not exact, so we will have a residual that we call delta. The second equation tells us that the actual deformation should be close to the external available reference deformations. But in general, if we can also assume that the actual deformation should be zero, if we have a large area, the actual deformation should be zero for most points. So by minimizing the residuals delta and delta prime of these two equations according to a given norm, for example, the L1 norm or the L2 norm, we can retrieve the calibration parameters and at the same time retrieve the components vertical, the three-dimensional components, typically two-dimensional if because now with polar satellite, we are not able to retrieve the north-south component of the actual movement, but this depends on the input data. In general, the method works with also for the third component. So we are able to retrieve everything, all combined, all at the same time. And in this sense, we can say that this is an optimal reconstruction. We tested this method on simulated data. We simulated realistic acquisitions for Sentinel-1, Cosmos SkyMed, and RadarSat satellites with realistic parameters. We also added the noise. And for the actual movement, we considered two Gaussian-shaped signals, one with a big spatial extent, the red one in this image, and one with a small spatial extent, the blue one here. We consider for the time evolution of this signal a cubic evolution, a cubic temporal evolution. We consider for the three satellites different spatial coverages, as you can see from the images on the left, and also different time intervals. And as you can see from the graphs, the x coordinates is the time. And for this reason, the colors are different because in different years, since the evolution is cubic, we have different mean velocities. This is the temporal evolution of the small Gaussian signal. And coming to the reconstruction, we see here in the fourth image, the first three are the input images. The fourth image on the right is the reconstructed mean velocity relative to the whole period. And on the graphs on the right, you see the temporal reconstruction on the two Gaussian signals. And you can see that the reconstruction is practically perfect. Now, this is the reconstruction of the horizontal component. Again, very good. So we obtain 0 as expected for the vertical component, for the horizontal component. We made also another simulation adding corresponding to each acquisition date a surface, a ramp, and different from each date and for each satellite.
Can you slowly round off, Mario?
Yes, we arrived at the conclusion. And again, we were able to obtain a very good reconstruction. In the overlapping areas, we were also able to reduce noise by the expected factor. So this concludes the presentation. And so we presented a method to combine together in an optimal way the InSAR measurements from different satellites and different independent processing. The method referred the different measurements to a common temporal and spatial reference, reconstruct horizontal and vertical components, the deformation, helps reducing large-scale systematic errors, reduce noise in the areas of overlap, and optimal integrate, when available, independent external measurements. Thank you. This concludes my presentation.
Thank you very much, Mario, for a very interesting talk. And indeed, I would like to remind the audience that you can ask your questions. We have several questions coming in. And after the next talk, which is the last talk of this session, we'll have a Q&A session in which we can discuss several questions to the authors. So the last talk is now given by Jan Yuan, and it is entitled Statistic Properties of Phase Inconsistencies over Different Land Cover Types. So Jan, please share your screen.
Yes, thanks, Ramon. Can you see my presentation now?
Yes, this is good. Yes, please start.
Thanks. Good morning, good afternoon, and good evening, everyone. Today I will present the statistical property of the phase inconsistencies. Let's start with the closure phase example we got over a vegetation area in South France. This image is formed by using Sentinel-1 vivid acquisitions in 3 different dates. The resolution of this image is 200 meters. You can see from the color of the images that closure phases are deviated from 0, and they illustrate a clear spatial correlation. By checking the land cover map over this area, the spatial correlated closure phase indicates a geophysical origin. The bottom right red area corresponds to the broad-leaved forest, while the blue area at the top left is intensive grassland. At the diagonal, the magnitude of closure phases are randomly distributed. This indicates noise. Similar images had also been reported by previous literature with data acquired range from P-band to X-band. To make things more clearer, let's talk about the definition of closure phase and phase inconsistency. What is the closure phase? To form a closure phase, we need to have 3 SAR images over the same area, but acquired at 3 different times. Interfere these 3 images with each other, we can get 3 interferograms. Then we combine the phase of each interferogram in a circular way to get a closure phase. When the closure phase is deviated from 0, we will call it phase inconsistency. There is a common and fundamental assumption in SAR interferometry, which states the phase is consistent. This statement is true in 2 aspects. Firstly, the SAR interferometric phase is geometrically interpreted, and this statement is also true at pixel level. It can be shown directly by math. But when we started to do the spatial averaging, the phase inconsistency problem rises. In most of the current literature, the explanation for the non-zero closure phase is noise. However, when you average enough, the expected value of thermal noise is 0. It is clearly not what we see from the previous example. So what makes the closure phase deviated from 0? It's an geophysical origin. Based on the above statements and the closure phase images we got, we make a hypothesis that geophysical non-zero phase closures are not the exceptional, but a rule. One might question, why are they largely unnoticed, particularly at C-band? This is because they are associated to low coherence, which needs enough spatial averaging to exploit. To convince you, I'll show you the phase inconsistency from observations and illustrate how often do we see the phase inconsistency and how significant are they in statistical point of view. The data we use is Sentinel-1 IW model acquisitions with 6 days time interval to form closure phase. There we got corresponding amplitude, coherence, and histogram of further analysis. Another data set is a land cover map over South France, and we choose for dominant vegetation over our research area to illustrate the phase inconsistency. This is land cover map over our research area. As indicated before, there are 4 main land cover types. The intensive grassland, which is mainly gray, and the natural grassland, which is mainly purple, and the coniferous forest and broad-leaved forest, which are gray. On the right-hand side is a corresponding vivid polarized amplitude image with 400-meter resolution. Comparing these 2 images, you could see the signature of different land cover types. The forest is bright, while the grassland are less bright, and they can be distinguished from each other. The brightness variation corresponds to the roughness and moisture changes. Let's post the previous closure phase example with 400-meter resolution again. Now it is clearer that the closure phase signature shows consistency with the land cover types. To statistically analyze the closure phase, we plot a histogram. This is a histogram example of 1 400-meter vivid polarized images. You can see clearly that the mean value deviates from 0, and the shape of the density plot is not symmetrical. This indicates that the probability density function is not normal Gaussian distribute. It will be more interesting to look at the time series. These are the histogram time series for both VV and VH polarized states. It is interesting to see there are differences between these 2 plots. Although both of them show the same signatures, but for VH polarization, the magnitude of the density is smaller. So to better illustrate the statistical behavior of different land cover types, we use the one with larger magnitudes, which is the vivid polarization. You can see the common feature shared in all the land cover type is that during summer, which is May to June, the closure phase deviated from 0 is smaller compared with other seasons. The reason behind it might be that the plants are drier and the soil and the moisture don't show significant changes. It is hard to see the difference between the intensive grassland and natural grassland because the reader is mostly seeing the ground, which indicates the soil moisture changes. But for forest, we can see the signal from the tree by comparing the broadleaf forest and the coniferous forest. You can see the phase inconsistency is more obvious in large-leaved forest, which relates to more violent moisture changes. And we are interested in what level of phase closure can be explained by phase noise, and when we believe the phase closure must be geophysical, we carried out a numerical model with the assumption that closure phases are solely contributed by noise. The input of the model are coherence of each interferograms, gamma 1,2, gamma 2,3, and gamma 1,3, and the number of loops n. Then we performed the Monte Carlo simulation. And finally, we got the output, the lookup table of estimated standard deviation of closure phase. On the right-hand side, this is an illustration of the model output with coherence 1,2 fixed as 0.5. It is obviously that magnitude of the estimated sigma CP is getting larger with lower coherence, which indicates the noise varies more violent. This reconfirmed the statement in our hypothesis that low coherence makes the closure phase largely unnoticed. This no data error is caused by square root computation in covariance metrics. Then how can we use this sigma CP? We divided the closure phase by sigma CP to get a significant ratio. As we assumed that the closure phase originates from both noise and geophysical changes, the significant ratio can be written in 2 parts. Here we make an assumption under the large number of loops that the phi noise would perform like a zero mean Gaussian distribution. And when we standardize it by sigma CP, it will be a standard Gaussian distribution. Meanwhile, the geophysical part won't change. Therefore, when we do spatial averaging to reduce the noise, the more we average, the higher the significant ratio. And also from the definition of the standard deviation, it is proportional to 1 divided by square root of number of samples. And here, the number of samples is the number of looks n. For example, with IW mode data, 400-meter resolution significant ratio is about 2 times larger than that of 200-meter resolution. To show you how does this significant test actually works, I get some images for you. This is a closure phase acquired at the first day of 2017, vivid polarized data with 400-meter resolution. And then we input the coherence and number of looks to the numeric model to get a sigma CP. Now we can compare the sigma CP with the coherence. And we can see the larger sigma CP corresponds to the lower coherence area and also corresponds to the high noise area at the diagonal. Then we can conclude that the low coherence and high sigma CP and high noise are closely related. Now we divide the closure phase by sigma CP. We can get a significant ratio, which shows the same pattern as the closure phase, but the noise in the diagonal area is less visible. And the magnitude, and you can see the magnitude of the significant ratio is largely deviated from 1. And we do the statistical analysis again. Let's revisit the definition of significant ratio first. It is a combination of noise and geophysical changes contribution. So here, I plotted a ratio histogram together with a standard Gaussian distribution, which is supposed to be the contribution of noise. Then we take a difference between these two histograms, which is a ratio histogram minus Gaussian histogram. I have to emphasize here that the difference is not a probability density function of the geophysical arranging closure phase. We do this operation just to be able to show a 2D time series. Let's see what we got. As we concluded before, the density plot features are more obvious in wavy polarization. And for the significant ratio, it will still be more violet than VH. Therefore, we still use the wavy polarized data to illustrate different land cover types. Let's take a look at the summertime again. There are more obvious features than closure phase density plot, which indicates the significant ratio enhances geophysical contribution signatures as we expected. The difference between natural grassland and intensive grassland becomes clearer, while the two forest behaviors becomes similar. So for setting the threshold to filter the noise, it will be necessary to take both the closure phase and significant ratio behavior into account. Now I will show you the most exciting part of this presentation, the animation of all the results. These are the animation of all the results of the year 2017. And the first one is the closure phase. And second one is the significant ratio, which reduces the noise in the closure phase. And the third one is the amplitude of the last day of each closure phase. It doesn't change, it is changing, but it's not changing very violent. And at the bottom are the coherence. Please enjoy this a bit. To wrap up, we conclude that we confirm the hypothesis we made before that the geophysical non-zero phase closure are not the exception, but the rule. And based on the results, they are the next step for our researches. Firstly, the statistical explore causal phase closures. For example, confirming the relation between soil moisture and explore relation with water dynamics in vegetation. And secondly, as we see different signature in copole and cross-pole data, so study the polarimetric closure phase signatures will be interesting. And thirdly, there exists some soil moisture model for both amplitude and interferometric respectively. As we can see the consistent feature in both observations, drawing to these models will be interesting. That's all for my presentation. Thank you.
Thank you very much, Jan, for this presentation. And this concludes the 5 presentations of this session. If I wrap up what I heard this morning, my conclusion is that for all 5 presentations, we're moving away from, let's say, only producing colored dots or colored maps, but we're really trying to interpret what we see. And all 5 authors have tried to do that in their different ways. So it's great to see that new algorithms and methods and technologies are being developed to accomplish that. So there have been several questions in the chat, and now it's time to discuss those. I would like to go through them in the order of the presenters, and I propose that I will read the question and then the presenter can answer them. So Alessandro, the first question here comes from Amin, who wants to ask whether the proposed algorithm, the algorithm that you presented, has a better functionality to increase PS density in comparison to running stems on the SBES mode. So could you comment on that?
I mean, first of all, I'm not presenting an algorithm. I'm just trying to recommend to the amplitude data. So I wouldn't comment on use amps or BAS, but wherever and whenever you run any multi-temporal algorithms, it's very important to provide also some measurements of the accuracy of what you provide. And indeed, some statistical figures you can immediately retrieve from the amplitude data analysis can be extremely useful. I would wrap up with the message.
Okay, thank you very much. Mark, a question from Homa, and that was on the contextual data where you showed spatial attributes, and the question was whether you also consider temporal attributes such as temperature, precipitation in the matrix, and also whether you applied queries on that.
Yes, the answer is yes. We are currently indeed trying to tackle the problem of incorporating temporally dynamic contextual information into the space-time matrix. We have several ways of doing this, but I think the most interesting is kind of in the machine learning domain, where we try to cluster our scatterers based on their time series behavior or their phase behavior over time. And then we combine these clusters with also temporal variable contextual information in that sense. And then I recommend to go back through the presentation of Philip Conroy yesterday, where he explained this method on how to use clustering algorithms to extract this temporal information from our scatterers. So yeah, that's the way we're heading with it.
Great, thank you. Alberto, a question for you. And the question, I'm not sure who asked the question, but the question is, would noise where sigma n changes as a function of coherence affect the monotonic increase in entropy?
So yeah, I think you mean if we have noise which is not Gaussian, but whereas with the spatial feature is this your question? Well, my guess is so. We haven't made such kind of experiment, but my guess is no. So fuzzy entropy it's just a measure of the variation of samples. So I think that it measures let's say locally how smooth a series is. So I think no, but however, we will sure try to delve into these questions in the future. So thanks for the insight. Yeah.
Okay, great. So, and I would like also to remind the audience that if you would like to contact the authors, the Umbrella stage has this opportunity to interact with people on a one-to-one basis. So, question to Mario, by Amin. How did you tackle the difference of sensors in the inversion step, so solving the L2 norm? And then the question was, did you use weighted least squares or least squares for component estimation or something else? So the difference of sensors in the inversion, how did you tackle that?
Well, there are many possible ways to solve the problem, the minimization problem I mentioned. Of course, if the question is about using weights, yes, we can weight different weights each single equation, depending on what you want to weight more or less, the reliability of each measurement of each equation.
Okay, good, thanks. And a question for Jan. Jan, in your study, you used the coherence as an indicator to calculate the significant ratio. And the question is, did you also consider other indicators than the coherence, such as, for example, the homogeneity of pixels? Question by Failu.
Yes, thanks. This is a very nice question. But for this study, we don't consider the homogeneity of the pixels, but we should, because it will also allow us to correct for the equivalent number of looks. That might be the next step of our research as well.
Okay, good. Then I'm going back to Mark. A question by Anurag. How can there be a scope of storing raster data in addition to vector data in your data model? How are you dealing with those two types of data?
That's a nice question. Basically, we can store our raster information separately in the spatial database. That's one way to do it, and then refer to it via our querying system. But the other way is to directly attach them to the scatterers by using point sampling tools, so that we can retrieve them directly by querying the scatterers themselves. But we can also do this in a buffering manner, where we per scatterer we create buffer zones around them to extract the relevant pixel values of a specific raster and attach this to the scatterers or group of scatterers. So I hope that answers your question.
Good, thanks. Yeah, I'll go quickly through to answer as many questions as possible before the coffee break. A question to Alberto from Homa. The fuzzy entropy is sensitive to the R parameter. And the question is how to tune this R parameter if you don't have a priori knowledge in wide area processing.
Yes, well, okay. If you see the medical literature from which we have taken this fuzzy entropy index, you see that the most used value for the DTR parameter is 0.15 or 0.2 times the signal variance. So, but we have made some further experimentation to check if also in the case of InSAR time series is the same, and the answer is yes, because actually what we are using here is only the fact that the fuzzy entropy increases with increasing noise. So actually, it is not so important which is the actual value, but only the fact that it is so it's decreasing with the frequency noise. So we actually use also the 0.2 value for simplicity.
Okay, thank you, Alberto. I'll do two more questions before we go to the coffee break. The one from Mario. That is a question from Richard. Your method assumes that points undergo the same motion as the nearby scatterers. And the question is, do you consider some consistency checks with the ground truth data? Is that question clear?
Yeah. Well, you know, as I mentioned, you have to, yes, you assume, yeah, you have to resample data. You have to assume that in the overlapping area, there are some matching points. So, yes, you assume that the points that you match have the same behavior. This is not a big problem because we are interested on retrieving large-scale effect, on calibrate the various data. So this is not a big problem if the match is not always perfect. So yeah, this is
okay. Okay, thank you very much. So the last question of this session comes from Iceland, from Shani. Have you looked at how different degrees of multi-looking may change the results? So the question is, did you always multi-look in the same way, Yuan? Or have you looked at how different degrees of multi-looking may change the results?
Yeah, I think this question is closely related to the previous one because we assume the area is homogeneous, but this should be improved.
Okay, concise answer, very good. Okay, so I think this wraps up the talk. It's 11 o'clock here at the Central European time. I think, Marcus, we're gonna go for a coffee break, right?
Exactly. Thank you for sharing, Ramon, and thank you for all the presenters.
Okay, good. So then we'll close the session, and after the coffee break, there will be the start of the parallel sessions. So there will be one on the troposphere and the ionosphere, and one on data products and services. And those will both start at 11:30 in half an hour. Thank you, all the speakers, and have a nice break.
Thank you.
Thank you.